In today's lesson, we're going to be looking at oblique, also known as slant asymptotes. So we had already discussed that given a rational function, we talked about vertical and horizontal asymptotes and how rational functions can have those. If you missed that lesson, I'll link it in the top right-hand corner. We want to talk about another type of asymptote known as oblique, or equivalently slant asymptotes. So these slant asymptotes occur for rational functions. And again, a rational function is just a polynomial in the numerator divided by a polynomial in the denominator. Slant asymptotes occur when the degree of the top is equal to exactly one more than the degree of the bottom. So you can see here in this example here, we can see that the degree of, let's denote the top as p at x, is 2, and you can see here the degree of the bottom, which we can denote as q at x, is 1. So in this situation here, degree of the top is exactly 1 more than the degree of the bottom. So we should have a slant asymptote here. So the question becomes is, how do you find slant asymptotes and what do they look like? Let's take a look at finding the slant asymptote for the following example. To find the slant asymptote, what you want to do is you want to divide the denominator by the numerator. Let's go ahead and do this using long division. Going through long division, we have the following decomposition. Now let's express this using the division algorithm. And you can see here our polynomial of degree 2 breaks up into the quotient times divisor plus your remainder. Now, again, we're interested in this rational function here, so I'm going to go ahead and divide across by x minus 5. Doing so, we get. So now we have our rational function is equal to 2x plus 3 plus 8 divided by x minus 5. And again, you can see here I divided across by x minus 5, and by doing so, we had cancellation here and here, and we have this following decomposition for our rational function. This decomposition here, you can see that now if I want to find my slant asymptote, much like horizontal asymptotes, the slant asymptotes occur on the outer bounds of your function. So by letting x get infinitely large or letting x get infinitely small, we can discover our slant asymptote. Notice as x gets infinitely large, the following rational function will approach 2x plus 3. The reason for that is as x gets infinitely large or infinitely small, we can see that 8 over x minus 5 will approach 0. Therefore, as x gets infinitely small or infinitely large, our rational function will then just approach the line 2x plus 3. And just to summarize this below, as x gets infinitely large or infinitely small, our rational function is approaching the line 2x plus 3, and that becomes our slant asymptote. Let's take a look at the graph of this rational function to view our slant asymptote. Looking at the graph of the rational function here, you can see the dotted blue line here represents our slant asymptote. This is y equals 2x plus 3. And then we have our rational function here. Let's label that r at x. These points right here, you'll notice that we have a vertical asymptote. It's not labeled, but we have a vertical asymptote here at x equals to 5. And you recall our rational function had a vertical asymptote at 5. These 2 points right here are the roots of the numerator of the function. So if you take a look, if you recall, the numerator of the function was equal to 2x squared minus 7x minus 7. Using the quadratic equation here, we get. And again, finding the roots of the rational function, you set your numerator equal to 0. Setting this equal to 0, I get 4.13 and negative 0.81 approximately. And these represent the roots here where your rational function is crossing the x-axis. So again, we have a rational function which has a vertical asymptote at x equals to 5. And now we have this new type of asymptote. You can see here the function y equals 2x plus 3. So as x gets infinitely large and gets closer and closer and closer to negative infinity, our rational function will get closer to 2x plus 3. All right, let's take a look at another example finding slant asymptotes. Following function here, we want to do the same thing. Again, notice here the degree of the top here is equal to 2. The degree of the bottom is equal to 1. So we have a situation of having a slant asymptote. Before we look to find slant asymptotes, let's find our x-intercepts, y-intercepts, and any vertical asymptotes the function may have. All right, finding my x-intercepts here, I set the numerator equal to 0. I went to go factor that. We saw the discriminant was less than 0, so there's no real roots, so this rational function will not cross the x-axis. Finding my y-intercept, I set x equal to 0 and got a y-intercept of negative 3. Vertical asymptote exists when x is 2, and there's no horizontal asymptote. You cannot have a horizontal asymptote and a slant asymptote at the same time. Now let's take a look at finding our slant asymptote through long division. Again, going through long division here, we end up getting the quotient is 3x minus 1. And when you express your rational function, in terms of that decomposition we had done in the previous example, you end up getting 3x minus 1 plus, again, 4 over x minus 2. Now, as x gets infinitely large or infinitely small, once again, this will tend towards 0. and our rational function will approach 3x minus 1. In general, when you're going through long division, it'll always be the case that your quotient will be your slant asymptote. So therefore, we have a rational function here with a slant asymptote at 3x minus 1. Let's take a look at the graph to see all these characteristics put together. All right, here's our graph for our function r at x. You'll see here again, the graph in purple, that's our rational function. It is approaching the line y equals 3x minus 1. It's never on the line. Again, with scaling issues, sometimes it looks like that in this case, but is not. And this does have a vertical asymptote at x equals to 2 as well. So that's kind of this line going up here. You can see that function is approaching negative infinity as we approach 2 from the left, and positive infinity as we approach 2 from the right-hand side. And notice that the rational function does not cross the x-axis, as we did not find any real roots. So this is an example of a rational function that has a slant asymptote at 3x minus 1. Let's take a look at another example. All right, let's take a look at the next example here. Again, same sort of situation. The degree of the top is 3, degree of the bottom here is 2. So you have the possibility of a slant asymptote here. So let's go ahead and find all the characteristics of the rational function that we know so far. Doing so, we get. So taking a look at this rational function here again, I want to go find the x-intercepts. If you go ahead and do the rational root test, setting the top equal to 0, you'll find the rational roots to consider are plus or minus 1 or plus or minus 1/5. None of those four will work. Further computer analysis here, we can find that the root is negative 0.3716 approximately. Again, sometimes you need computer software to get some of the sort of more difficult, challenging roots to find. At any rate here, you know that the degree of this was odd. We know it's going to cross the x-axis. It crosses at an irrational number. Moving on, I found the y-intercept. The y-intercept is negative 1/4. Again, you just evaluate the function at 0, in which case we get negative 1/4 for the y-intercept. Vertical asymptotes happen when the bottom is 0, in which case we can factor and we get roots at plus or minus 2. Again, you cannot have a horizontal asymptote with a slant asymptote, so there's no horizontal asymptote. Going through long division here, we find the slant asymptote is 5x. Now let's take a look at the graph of this rational function. Graphing this rational function here, you can see we have our slant asymptote here at y equals 5x. Again, very steep linear relation. And again, your rational function is approaching this linear relation. As we get larger and larger values or smaller and smaller values, this rational function will get closer and closer to the line y equals 5x. We also have our x-intercept here, which is approximately at negative 0.37. And you can see here that our function, again, has the vertical asymptotes both at positive 2 and negative 2. And again, due to the scaling of these graphs here, as there's a lot to show on a specific grid, it's hard to kind of get everything on perfectly, but you do have vertical asymptotes at plus or minus 2, which are not drawn here. So you can see here that our rational function is approaching positive infinity as we approach 2 from the right-hand side, and it approaches negative infinity as we approach 2 from the left-hand side. On the other hand, you can see as we approach negative 2 from the right-hand side, our rational function is approaching positive infinity. And as we approach negative 2 from the left-hand side, our rational function is approaching negative infinity. So this is a graph of a rational function with a slant asymptote at 5x, and it has vertical asymptotes at x equals to 2 and x equals to minus 2. One important observation here I'd like you guys to make is notice you can actually cross the slant asymptote. Again, the slant asymptote only exists as x gets infinitely large or infinitely small. So locally, for finite values, your graph, your function, your rational function can cross a slant asymptote. The same can be said about horizontal asymptotes. A function can cross a horizontal asymptote, but as x gets infinitely large and infinitely small, that rational function will either tend towards its slant asymptote, like we have here, or towards its horizontal asymptote, as we talked about in previous examples. So you can cross slant and horizontal asymptotes, and this is one example of crossing a slant asymptote because, again, that cross happens, the function is defined here, and you can cross at this value. The only way we came about finding a slant asymptote of 5x was by letting x get infinitely large or infinitely small. All right, that concludes today's lesson on graphing rational functions with slant and oblique asymptotes.